Hello everybody! Today we'll be going over problem 3 in the USACO Silver Division from the 2016 February contest Milk Pails. Farmer John has a target value of M he's trying to reach, and he has 2 pails of X and Y capacity. In order to get to M, he can perform 3 different operations. Fill each bucket, empty each bucket, and pour one bucket into the other. He can perform up to K of these operations. It may be impossible to actually reach M, so Farmer John wants to reach a value as close to M as possible. He wants to know the smallest possible difference between the target and the milk in the pails within these K operations. Let's take a look at what the operations look like. Suppose both pails have some random amount of milk in them. Filling just means setting one's milk to its capacity. For emptying, one's pail is just set to 0. For pouring, we have 2 cases. Either all the milk can fit into one pail, so all of it goes into one pail, or all of it cannot fit into one pail, so one pail is filled and the other receives the leftovers. Now let's take a look at the sample case. We have a pail with a capacity of 14 and a pail with a capacity of 50. We can perform up to 2 operations and we're trying to get a target milk of 32. For the sample case, we can just fill the 50 pail, as that means there is a target value of 32 and 50 milk in the pail. As a result, we get a difference of 18, which aligns with the output. So let's take a look at some observations we can make. We have 3 types of operations, and each operation can happen to either pail, so we get 6 total options for each of the K transitions. We have a limited number of combinations for the milk in the pail, since they're lower bounded by 0 and upper bounded by x plus y. We can try to reach each one of these values, keeping track of which is closest to m every time. So how exactly do we find these values? Well, we have 2 ways we can use to simulate all 6 operations for each of the K transitions, DFS and BFS. However, one of these happens to be more optimal, and that one is BFS. First, let's go over why DFS is naive. We apply all 6 operations each transition, and we'll use a 3D grid with size x plus 1 by y plus 1 by k plus 1. We need the plus 1s because the values range from 0 to x or y, meaning there are x plus 1 or y plus 1 possible values for each pail. K plus 1 is there to handle the original state of no transitions. We need 3 dimensions because we need to track the exact number of steps taken to get to each xy pairs for reasons that I'll explain in a moment. Since the sample case was rather short, let's suppose x equals 5, y equals 7, and k equals 3. First, both our pails are empty, so we'll set x equals 0, y equals 0, and k equals 0 to visited, since this is our initial state. Our order of operations is going to be fill x, fill y, empty x, empty y, pour x into y, and then pour y into x. Here, we can now start our DFS from the first state. At the first operation, we fill x, and then we have to go down and fill x again, since DFS will try to complete a whole branch before moving on. After that, we fill x again, and we finally reach k equals 3. Then we need to fill y, and then we'll backtrack to k equals 2, fill y there, and then try to fill x and fill y again. We see a lot of repeats here, which is why DFS isn't efficient, but none of these duplicates will pose a major issue. Now we're going to try emptying. We empty x and then we empty y. So far there's still no issues, however the pair of x equals 0 and y equals 7 is the reason why we need 3 dimensions. I'm going to skip a few steps now, but at k equals 1 we can also just fill y. So we see that we have a duplicate value that's appearing before in terms of operations, but after in terms of the DFS. So the reason why the DFS is naive is because we need 3 dimensions because the number of steps taken to get to a cell matters. Take the cell 07. It was visited in both transitions 1 and 3. The DFS will complete a single pathway at a time before moving on to other options, so 3 will be calculated before 1. Thus, if we use the 2D grid, transition 1 would be discovered after the one in transition 3, and we would skip it since it'd be marked as visited. However, this doesn't take into account the fact that we took 2 more steps to get there. Thus, this inaccuracy causes issues because we may have needed those steps between to get to a lower m minus m prime. We have no choice but to revisit cells, and thus we get a time complexity of O of x times y times k, as at the worst case, each transition may reach each possible xy pair. Now let's get into why our BFS is more optimized. With BFS, we can use just one 2D grid for all xy pairs. If a calculation has been completed, we know we did it in the least number of steps possible since BFS visits cells as soon as it can. We can avoid revisits because of this guarantee, and thus our time complexity is only x times y, as at the worst case, each xy state is calculated once. Let's take a look at how this works. Initially, we have 0, 0 marked as visited. After transition 1, we can fill both buckets individually as the other operations have no effect. For transition 2, from x equals 0 and y equals 5, we pour x equals 5 into y. For x equals 5, y equals 2, we pour y equals 7 into x. For x equals 5 and y equals 7, we fill either empty bucket from transition 1. At transition 3, we get x equals 0, y equals 2 by emptying x at x equals 5, y equals 2, and we get x equals 5, y equals 5 by filling x at x equals 0, y equals 5. These 8 states are all only visited once, meaning it is more efficient than the DFS. Now let's take a look at our implementation. We read in our 4 variables, and then we push our initial state into the queue. We then start our BFS. We perform all 6 operations each time, and if a cell has been visited, we can safely skip it. For each XY pair, we keep track of the minimum difference between the target and the milk, and then we output the minimum. The time complexity is thus only O of x times y because each pair is only calculated once, and the memory complexity is O of x times y because we use a 2D grid with those dimensions to track visits. That's the general explanation done. Now I'll go over language-specific solutions for C++, Java, and Python. Let's take a look at the C++ implementation for this problem. We define our 4 variables, the 2 Pails, the number of operations, and our target, and we read them in. After that, we define our result. We can initialize it to m since both Pails start with nothing, so there's just a difference of m. After that, we create our 2D visited grid, which stores every pair of the amount of milk in either pail. We set the empty state of 0, 0 to visited, and then we define our queue for BFS. We'll be using a simple state struct, which stores the number of operations taken to get to this pair, the amount of milk in x, and the amount of milk in y. We'll push the initial state into our queue. Now let's get started on our BFS. While the queue is not empty, we'll take in the data of the current state, and then we'll pop it from the queue. We'll update result if the difference is smaller, then we'll check if k operations have been done. If they have, then we'll have to continue as we cannot go any further. Then let's get started on our 6 operations. First will be fill. This is fill x, this is fill y. We just set the amount of milk in the x pail to x, and the same for y. We do the same logic, checking if they've been calculated before, and if not, we mark them as so, and then push them into the queue. Next we have the empty operation, which instead of x or y, sets them to 0. After that, we have our pour function. This one is pour x into y, where we compute the leftover. If there's a negative leftover, it means all the milk can be stored in one pail, so we empty one and put it all into the other. Otherwise, we leave the leftover in one pail and set the other to its limit. For pouring y into x, we follow a similar logic, checking if the leftover is negative. If so, we push all of the milk into one pail and empty the other. If not, we fill one pail and set the other pail to the remainder. Finally, we print our result. That's all for the C++ implementation. Now we'll take a look at the Java code. Now let's take a look at the Java code. We read in our 4 variables, the capacity of pail x, the capacity of pail y, the number of operations we can do, and the target value we're trying to reach. After that, we initialize result to m. Since both pails are initially empty, there's a starting difference of m minus 0, which is equal to m. After that, we'll define our visited grid, which checks if each xy pair has been calculated before. We'll set the initial state of 0, 0 to visited, and then we'll define our queue. We'll use a simple state class to track how many operations have been done to get to this point, the amount of milk in pail x, and the amount of milk in pail y. After that, we'll add the initial state of no operations and no milk in either pail to the queue. While the queue is not empty, we'll take out the current state, and then we'll update result if the amount of milk in the pails now is more optimal. If we've used all k of our operations, then we need to continue, otherwise we'll move on with the BFS. We'll start with the fill operations. If the state of filling x or filling y has not been visited, we mark them as visited and then add them to the queue. Emptying follows a similar logic, except instead of setting to x and y, we set them to 0. Finally, for pouring, we'll calculate how much milk would be left over if we were to pour all of it into the other pail. If it's negative, it means that the pail can hold all of the milk, so we empty the first pail and then put all of the milk in the second pail. If it's positive, it means the other pail cannot hold all the milk, so we set it to its limit and put the leftover back in the original pail. This code is for pouring x into y, and then we just reverse the letters for pouring y into x, following an identical logic. After all 6 operations have been done for all k transitions, we can print our result. That's all for the Java code. Now let's take a look at the Python solution. Let's take a look at the Python solution. First, we'll read in our 4 variables the capacity of the 2 pails, the number of operations we can conduct, and the target milk value we're trying to reach. After that, we'll set our result, which stores the minimum difference, to m, as since both pails are initially empty, there's a starting difference of m minus 0, which is equal to m. After that, we'll define our visited grid, which tracks if each pair of x or y has been visited yet. We set the starting value of 0, 0 to visited, and then we define our queue. And then we push the starting state into the queue, which will be in the order of the number of operations taken to get to the current state, the amount of milk in pail X, and the amount of milk in pail Y. While the queue is not empty, we take out its current value, and then we update our result if there's a smaller difference. If we've exhausted all k operations, we need to continue, otherwise we'll move on with the BFS. First will be the fill operation. We simply set either the X bucket or the Y bucket to its capacity, and then check if it hasn't been visited. If so, we mark it as visited, and then we push it into the queue. The code for emptying a pail is similar, except instead of setting it to the bucket's limit, we set it to 0. For pouring X into Y, we set pour X equal to A plus B minus Y. If it's negative, it means all the milk can fit into one pail, so we'll put all of it into one pail and empty the other. If not, then we set one pail to its limit and the other to the leftover. Pouring Y into X follows a similar logic, except we flip our letters. If pour Y is negative, we push all the milk into X and then empty Y. If not, we fill X to its limit and then put the remainder in Y. After that, we print our result. That's all 3 language solutions done. Thank you for watching this video.